Hello everyone, I'm Ryan Keeley, a postdoc at UC Merced. In this talk, I will discuss various assessments and investigations into the DESI preference for evolving dark energy. I do these investigations using my transitional dark energy model and answer questions like, does the preference for evolving dark energy depend on the CPL parameterization? And no, it doesn't. Also questions like, what is happening with the data that gives rise to this preference, and how we can test the preference on future datasets, like for example using the growth rate of structure. So in general, I'm interested in testing the Lambda CDM model. So I try to pull it apart and see where it breaks. This model is pretty remarkable, and they can explain a bunch of pretty novel physics with just 6 parameters, from inflation to BBN to recombination to reionization, the growth of large-scale structures, and to the late-time acceleration of the universe. So it's pretty non-trivial that these 6 parameters fit the diverse datasets at all. And there are a few different ways to pull out the Lambda CDM model, and its assumed GR, but today I'm going to be focusing on testing the lambda part by measuring low redshift distances, and also the growth rate parts. So the DESI preference for evolving dark energy comes in the form of a CPL W0 WA model, and the region of dark energy parameter space is interesting since W0 is greater than -1 and WA is less than 0. By a large enough value, such that the parameter space prefers a dark energy that starts out in a quintessent regime and crosses into a phantom regime. So the significance of this kind of preference ranges from 2.8 to 4.2 sigma, depending upon which supernova compilation you use. And this is further interesting, basically, because there are theoretically good reasons why such a phantom crossing shouldn't be allowed. The parameterization that I use to do all these tests is what I call the transitional dark energy model. So the important parts of it is that it allows for a rapid changes in the equation of state, but also changes like that in the CPL kind of model. The transitional dark energy is preferred over Lambda CDM using this analysis at the 3.8 sigma level with the DES supernova and a weaker 2.4 sigma when using the Pantheon plus. So this corroborates findings of the DESI Collaboration, who found that their baryon acoustic oscillation data preferred evolving dark energy when fit to the CPL. So what is actually shown here are samples of W of Z drawn from the posterior of the TDE fit to the CMB plus DESI plus DES supernova datasets. Each of these samples are color-coded by how well they fit the data. So yellow corresponds to the best fit, and blue corresponds to a 2 sigma limit. You can see how the best fit prefers W of Z functions with rapid transitions around redshift of 0.5 and includes W of Z functions with more gradual CPL-like functions and functions that remain quintessent for much higher until much higher redshift. So the point being that essentially the preference for evolving dark energy is not an artifact of the CPL parameterization itself. Speaking of 2 sigma, I'm now going to explain how I calculate the 2 sigma limit that I mentioned in the previous plot. So starting from the beginning, common ways Bayesians calculate a 2 sigma limit is to plot the joint 2D posterior of the various combinations of parameters in a triangle plot, and draw a line around the contour that contains 95% of the points from the chain in that 2-dimensional space. For say W0 WA, for example, then if -1, 0, i.e. Lambda CDM, were outside of that contour, then Lambda CDM would be rejected at 2 sigma. This of course leads to projection effects, especially when the posterior is non-Gaussian, and especially if the full n-dimensional posterior is non-Gaussian. And there's of course no reason to expect such an n-dimensional posterior to be Gaussian. But what you really want instead of these 2D posteriors is you want the contour that contains 95% of the posterior in the full n-dimensional space, not just the 2D projections. To be more specific, we want the likelihood or chi-squared contour that contains 95% of the posterior, and since the chi-squared values only increase the further out you go, finding the contour in terms of parameters can be written in terms of the contour of the chi-squared. This is the basic insight of nested sampling, by the way. So in the distribution that I'm plotting here on the page, so in this distribution, the chi-squared value at which 95% of the samples are better than it, then that is the chi-squared value of the 2 sigma contour. And if Lambda CDM has a worse chi-squared than then Lambda CDM is outside of the 2 sigma contour and is thus rejected at greater than 2 sigma confidence. And so that's what's plotted here. So you see two black lines labeled, showing lambda CDM is outside of the 3.8 sigma confidence level, and another showing where the 2 sigma confidence level lies. And I use this 2 sigma chi-squared value basically to do the color coding in the previous plots. Basically, every sample that has a better chi-squared than that 2 sigma chi-squared is basically within the 2 sigma confidence level. So just as further aside, you basically can't solve these kind of projection effect problems by switching to frequentist statistics either. You're basically just changing the interpretation of significance and still not really solving anything about projecting down from n dimensions to 2D or 1D distributions. So just a quick aside before we move on, I thought it was worth pointing out that this kind of evolving dark energy is not a solution to the H0 or S8 tensions. As you can see here, in the top is basically the posterior of my various transitional dark energy fits to both the essentially the predictions for S8 given these chains for using either the DES or Pantheon plus datasets. Basically the CMB plus DESI plus DES posterior is still relatively far away from the KIDS 1000 kind of posterior. I mean, it's still at the sort of 2 sigma level of tension, basically if you didn't have evolving dark energy. So there's no real meaningful shift using this evolving dark energy. And more simply, in the bottom panel you see the posterior for H0. The posterior for H0 still prefers the same CMB only kind of H0 values, and so hence this evolving dark energy does not solve the H0 tension. It's not like any really expected it to anyways. Now I will discuss how to test evolving dark energy models using future datasets, namely growth rate datasets. So as you can see in the equation here, modifications to the expansion rate will necessarily modify the growth rate. So evolving dark energy will have a different shape to the growth rate history than Lambda CDM. So we show here the predicted distribution of F sigma 8 values drawn from the TDE posterior fit to the CMB plus BAO plus supernova datasets, and in red are the recent DESI F sigma 8 data points coming from redshift space distortions. As you can see in the plot, compared to the Planck Lambda CDM curve in black, at redshifts above z equals 1, the best fit TDE parameters predict the same values for F sigma 8, but at redshift less than 1, then the curve has a different shape. So between 0.25 and redshift 0.75, the dark energy density, and thus h of z, is higher in TDE than in Planck Lambda CDM. As you can see here, zoomed in, basically here I'm just dividing out the Planck Lambda CDM values. The higher dark energy and hence higher h of z decreases the growth rate of structure at those redshifts, as predicted by the equation on the previous page. But in contrast, by redshift 0, the dark energy density and hence the expansion rate of the TDE parameterization is smaller than in Planck Lambda CDM model, causing the growth rate in the TDE parameterization to increase relatively. So on the whole, this makes F sigma 8 as a function of redshift flattered with respect to the best fit Planck Lambda CDM model. So the DESI white paper predicts or forecasts that around 3% errors on the F sigma 8 measurements over multiple redshift bins. And basically in the redshift bins where the TDE predicts different values than Lambda CDM. Point being, future DESI RSD datasets can be an independent test of this evolving dark energy idea compared to just the BAO plus supernova plus CMB alone. Essentially, growth can be a test for preferences or modifications to the background itself. And therefore, importantly, this flattening of the F sigma 8 curve may likely be detectable. So here I'm going to discuss this plot, which I made in order to help build intuition about what's going on with the data and why the data prefers evolving dark energy. So what are shown in the colored contours here are the posteriors of the TDE fit to the CMB plus DESI in green, and then CMB plus DESI plus DES, and CMB plus DESI plus Pantheon plus in blue and orange respectively. And the gray lines show the curves with fixed h0 values that keep the angular diameter distance to the surface of last scattering, dA of z star, constant in the w is equals 0 and w z equals 1 plane for the CPL parameterization. And this demonstrates the impact of the CMB and how the mirage appears. We have used the CPL parameterization because it uniquely specifies a curve in this plane for fixed h0. The CMB only constraints for the CD parameterization follow these CPL curves. So the point being that the CMB alone allows for entire families of evolving dark energy curves. And so when h0 is equal to 67.36, as in the Planck best fit, which is shown in black, you can see that the w is equals 0, w is equals 1 curve passes through -1, i.e. lambda CDM. The other points in this line are those that would most closely mimic a lambda CDM model without including any sort of high-quality measurements of the low redshift distances, i.e. supernova or BAO. For values of h0 that are larger than about 65, most of the curves lie in the region of wz equals 0 greater than -1, and w of z equals 1 is less than -1, i.e. a region where phantom crossing is generic. So this plot and variations of it are useful for assessing the origin of the preference for transitional dark energy or evolving dark energy in general, and particularly in relation to specific datasets. So recall that if a cosmology is constrained by the CMB, that it needs to give the right angular size subtended by the sound horizon. So assuming no change to the sound horizon to the surface of last scattering, this is a tight constraint on the angular diameter distance to the last scattering surface. This can produce a mirage of W equals -1 dark energy while having a strongly evolving dark energy subject to certain constraints. So the mirage requires that in order to satisfy the distance at the surface of last scattering for models where W of z is where W of z equals 0 is greater than -1, then W of z must be less than -1 at some higher redshift, and vice versa. The CMB constraint alone selects a family of W of z functions that have this feature. However, both of the supernova datasets show a preference for W of z equals 0 greater than -1, and so necessarily W of z greater than 1 must be less than -1. Thus, we can conclude that the preference for evolving dark energy arises from a high-quality, low redshift measurement of the expansion rate. Both of the supernova datasets prefer that W at z equals 0 is greater than -1. The BAO dataset, calibrated by the CMB sound horizon, prefers h0 values between 70 and 65, and thus that the CMB's angular diameter distance sets the evolution of WA, how W changes with redshift. For example, in, say, a constant W of z model, i.e. WA is equal to 0, such a model would still want h0 to be 67.7 or so, and thus the CMB constraint puts us along the black line that intersects close to W is equals 0, W is equals 1, both being equal to -1. And so hence if you don't allow for an evolution in W of z, then you're artificially getting yourself close to lambda CDM. This may seem to be a coincidence, but the fact that a constant W of z model prefers W equal to -1 does not by itself illuminate the question of whether the CMB plus DESI plus supernova preference for evolving dark energy is robust. It is worth noting in this regard that the DESI and supernova contours have different slopes, and neither follows the CMB curve exactly, demonstrating the fact that they are adding independent information about dark energy and whether or not it changes with time. To further build intuition about what is happening with the data in these evolving dark energy models, I am plotting here the normalized residuals, that is, the residuals divided by their errors. If a model is a good fit to the data, then they should scatter like a normal variable around 0. Some have argued that the most discrepant points in lambda CDM fits are outliers, but if one were to exclude them, then the remaining points would make the residuals scattered by too small a degree. In contrast, if fit to a TDE or evolving dark energy model, then the residuals look drawn from a normal distribution, which is what we want. We can play the same game with the supernova residuals, and as you can see here, moving from a lambda CDM to a TDE model makes the residuals more close to a normal distribution. And for both the BAO and supernova datasets, the model is performing work, as in improving the fits, at the same redshifts. indicating that the BAO and supernova are telling consistent stories. One last point I want to make is, what is the preference for these evolving dark energy models that have phantom crossings over purely quintessent models that are never phantom? One representative thawing quintessent model is the PAD-W model, which fits the CMB plus DESI plus supernova datasets better than Lambda CDM, but not as well as CPL. And so I'm answering the question here, how significant is the data's preference for CPL over PAD-W? How significant is the data's preference for a phantom crossing over purely quintessence? I do this by generating 1,000 mock CMB plus DESI plus supernova datasets generated from a PAD-W model, and then fit both the CPL and PAD-W models to those datasets, and then plot the distribution of the delta chi-squared values for those realizations. In only 3% of the mock samples is CPL a better fit to PAD-W by a degree as large as seen in the real data. This means that the CPL and phantom crossing dark energy is preferred by the real data at more than 2 sigma over purely quintessent models. And so that brings me to my summary, where I want to highlight again that the DESI preference for evolving dark energy does not depend specifically on the CPL W0WA parameterization, e.g. TDE works as well. Further, that there are no outliers in the DESI data. The supernova and BAO residuals shift at the same redshifts, indicating that they're telling the same stories. The Z less than 0.1 supernova are driving the difference between DESI and Pantheon plus, but the preference for evolving dark energy is there regardless. It's not a coincidence in parameterization or weirdness in any one data sets that the evolving dark energy model are preferred. And further, I want to point out that phantom is preferred over quintessence at 2 sigma, which is in some sense only 2 sigma, but future datasets will help us make the difference more robust. Thank you all for listening, and I look forward to your questions in the actual conference.